You've been there before. You're deep into a conversation with an AI, maybe a chatbot or a virtual assistant, and you ask a follow-up question. Suddenly, it's like you're talking to a goldfish. It has completely forgotten what you were just talking about. It's a frustrating and almost comical reminder that for all their power, these digital minds have a memory problem. We see AI doing incredible things, generating breathtaking art, writing complex code, even composing music. But at the core of all this intelligence lies a surprisingly fragile component. It's memory. It's not like our memory. It doesn't hold on to experiences or build a continuous story of its existence. At least, not yet. The AI's memory is more like a temporary sketchpad, constantly being erased and redrawn. This single, fundamental limitation is the invisible wall holding AI back from its true potential. It's the reason they can feel so brilliant one moment and so bafflingly dumb the next. The quest to solve this memory problem is one of the most critical and fascinating frontiers in all of technology. It's a race to build a mind that doesn't just calculate, but remembers. And to understand the sheer complexity of this challenge, we first need to look inside the AI's mind and see the different, and often bizarre, ways it tries to remember its world. The most common form of memory you'll encounter in today's AI, especially in large language models like ChatGPT, is what we can call short-term memory. But a more technical and descriptive term for it is the context window. Imagine you're having a conversation, but you can only remember the last few sentences that were said. Anything before that is just gone. That's essentially how a context window works. When you interact with an LLM, it loads your prompt and the recent conversation history into this temporary workspace. This is its entire world for that moment. It can see the connections, understand the follow-up questions, and maintain a coherent dialogue, but only within that limited window. The model isn't truly learning from the conversation in a permanent way. It's just processing the information currently in its view. Think of it like a spotlight in a dark room. The AI can only see and interact with what's inside the beam of light. Everything else is in darkness. As the conversation moves forward, the spotlight moves with it, and the things that were at the beginning of the conversation fall back into the dark, forgotten. This is why you can have a great in-depth discussion with an AI. But if you bring up a detail from the very beginning of a long chat, it might have no idea what you're talking about. The context window has moved on. The size of this window is a huge deal in AI development. A larger window means a better short-term memory, allowing for longer, more complex conversations. But it also requires immense computational power. It's a constant trade-off between capability and cost. This reliance on a fleeting, temporary memory is the primary reason AIs can feel impersonal and forgetful. But what about the vast knowledge they seem to possess? The facts, figures, and concepts they can recall instantly. That comes from a completely different and much more permanent type of memory. And to understand that, we need to go back to the very beginning, to how these AI models are trained in the first place. If the context window is the AI's conscious thought, then its long-term memory is buried deep in its subconscious. This is what's known as parametric memory. It's not a memory of experiences or conversations, but a memory of patterns, facts, and relationships learned during its intense training process. Before an AI like a large language model is ever released to the public, it undergoes a training phase that is almost incomprehensibly vast. It's fed a massive data set, a significant portion of the internet, books, articles, and more. During this process, the model isn't memorizing text word for word. Instead, it's learning the statistical relationships between words and concepts. It learns that Paris is often associated with France, Eiffel Tower, and baguettes. It learns the rules of grammar, the nuances of tone, and the structure of a good story. All of this knowledge gets encoded into the model's parameters, billions of tiny numerical values that form the very architecture of its neural network. This is the AI's dream library. It's a static, unchanging repository of everything it learned during its childhood. When you ask it, "What is the capital of France?" it's not recalling a specific time it learned that fact. Instead, it's navigating the complex web of its parameters to generate the most probable answer based on the patterns it has internalized. The strength of parametric memory is its vastness and speed. It gives the AI a foundational understanding of the world. But it has a major weakness. It's frozen in time. The AI's knowledge is only as current as its last training date. It can't learn new things from its interactions with you. It doesn't know about yesterday's news unless its creators specifically update it. This creates a fundamental disconnect. An AI with a vast library of book smarts, but no ability to remember its own life experiences. To bridge this gap, engineers had to get creative and design a way for AI to take notes. This led to the development of a technique that acts like an external brain for the AI, a way to cheat its memory limitations. So we have an AI with a great but static, long-term memory and a very limited short-term memory. How do you give it access to new, up-to-date information without having to retrain the entire model, which is an incredibly expensive and time-consuming process? The answer is a clever workaround called Retrieval-Augmented Generation, or RAG. Think of RAG as giving the AI an open-book test. Instead of relying solely on its pre-existing parametric knowledge, the AI is given the ability to look things up in an external database before it answers your question. Here's how it works. When you ask a question, especially one that might involve recent events or specific data, the system first searches a connected knowledge base. This could be a curated set of documents, a company's internal wiki, or even a live feed of news articles. It finds the snippets of text that are most relevant to your query. Then, it takes your original question and a couple of these relevant snippets and feeds them together into the large language model. It's essentially saying, "Here's the user's question, and here are some notes that should help you answer it accurately." This process is a game changer. It allows the AI to provide answers that are grounded in specific, verifiable facts, drastically reducing the chances of it hallucinating or making things up. It's why you can ask an AI about the winner of last night's game or the current stock price and get a correct answer. It's not because the AI knows this information in its core memory, but because it knows how to find it. RAG is a powerful tool for making AI more accurate and reliable. But it's still a workaround. It's a way of augmenting memory, not truly creating it. The AI is a brilliant researcher with a perfect note-taking system, but it still lacks a personal, continuous thread of experience. To achieve that, we need to look at a system inspired by the human brain itself. And that brings us to the fascinating concept of attention mechanisms, which revolutionized how AI decides what's important enough to remember. In a crowded room, you can tune out the background chatter and focus on a single conversation. When you read a sentence, you instinctively know which words are the most important for understanding its meaning. This ability to selectively focus is a cornerstone of human intelligence. And for a long time, it was a missing piece in the AI puzzle. Early AI models processed information sequentially, treating every piece of data with equal importance. This was inefficient and often led to a loss of context, especially in long sentences. The breakthrough came with the invention of the attention mechanism, An attention mechanism allows an AI to weigh the importance of different parts of the input data. When processing a sentence, for example, it can learn to pay more attention to the subject and the verb than to the connecting words. It gives the model a sense of focus. Imagine translating the sentence, "The cat sat on the mat." When the model is generating the translated word for sat, the attention mechanism allows it to look back at the entire input sentence and decide that cat is the most relevant word to focus on at that moment. This is a simplified example, but it's the core idea. This ability to dynamically shift focus was the key innovation behind the transformer architecture, the foundation for virtually all modern large language models. Instead of a single plotting memory unit, transformers have multiple attention heads, each capable of focusing on different aspects of the input data simultaneously. It's like having a team of analysts, each looking at the same information from a different angle to build a richer, more complete understanding. Attention mechanisms gave AI a more dynamic and flexible form of working memory. It's how they can handle complex grammar, understand pronoun references, and grasp the subtle nuances of language. But even this advanced focus is still largely confined to the immediate task. To build an AI that truly learns and grows from its experiences, researchers are now looking beyond just augmenting memory and are trying to build it directly into the AI's core architecture. What if, instead of just giving an AI a notepad, you could surgically graft a perfect external hard drive onto its brain? That's the core idea behind a fascinating and experimental field of AI research: Memory-Augmented Neural Networks, or MANNs. Unlike the other methods we've discussed, MANs are designed from the ground up to have a dedicated, external memory component that they can learn to use. The network has a controller, which is like the core processor, and it's connected to a memory bank. The controller can perform two fundamental actions. It can write new information to the memory, and it can read information from the memory. Crucially, the AI learns how and when to use this memory on its own. Through trial and error during its training, it figures out what information is important enough to save for later, and how to retrieve the right memory to solve a new problem. This is a step closer to how biological memory works. We don't just store everything. Our brains learn to prioritize and store information that is likely to be useful in the future. MANs attempt to replicate this process. The potential here is enormous. An AI with this kind of memory could learn a task and then store the successful strategy in its memory. When faced with a similar task later, it could recall that strategy and apply it, allowing for much faster and more efficient learning, a concept known as one-shot learning. It could build a persistent knowledge base from its unique interactions, truly remembering a user from one conversation to the next. While MANs are still largely in the research phase and not as widespread as techniques like RAG, they represent a fundamental shift in how we think about AI memory. They are a move away from clever workarounds and towards building a more integrated and holistic artificial mind. This journey, from the simple context window to these complex, brain-inspired architectures, is all part of the grand challenge of building an AI that doesn't just process information, but truly understands and remembers its place in the world. The story of memory in AI is a story of evolution. It began with a simple, fleeting awareness, a digital goldfish swimming in the tiny bowl of its context window. It then developed a deep, subconscious library of knowledge, a vast but static understanding of the world. From there, we've given it tools to look outside itself, to read from our libraries and ground itself in our facts. We've even taught it the art of focus, the ability to see the important details in a sea of noise. Each step has been a leap forward, bringing us closer to an intelligence that feels less artificial and more intuitive. Yet, the final frontier remains: creating a persistent, unified memory. A memory that allows an AI to build a continuous narrative of its existence, to learn from every interaction, and to grow not just in knowledge, but in experience. Solving the memory problem isn't just about building better chatbots or more accurate search engines. It's about unlocking the next level of artificial intelligence itself. It's about building a mind in the machine that can't just answer our questions, but can remember them, learn from them, and maybe one day, truly understand them. The mind that remembers is the mind that learns, and the mind that learns has no limits. If you found this look inside the AI mind fascinating, consider subscribing for more deep dives into the technology that is shaping our future. Thanks for watching.